All right, folks. So I want to go over kind of just some basic terminology and ideas because, in all honesty, there's a lot of confusion between some words that we use in everyday life, like position and distance and displacement, for instance, because most of the time, kind of out in everyday life, you can kind of use those three interchangeably and you're fine. But in a class like an AP physics room, we definitely have some significant differences between them. But before we really get into it, I actually have a riddle to tell you. So we'll kind of start with a riddle, and I want you to see if you can figure it out. So I like to kind of go bird watching and photograph nature sometimes. And so I go outside one day and I have my camera, and I hope you can kind of follow along with this, kind of visualize it. So my front door faces south. So I walk out the front door, okay, and I go a mile south, and I'm walking along. I'm going perfectly south. I go, great, just straight out the front door. Awesome. And I'm walking along, and I see some birds. I'm like, oh, that's awesome, cool. I see an eagle, or I see some other kind of birds, and I take some pictures, and then I turn right. Okay, so I was going south a mile. I turn right. All right, so now I'm going west. I go west a mile. All right, and as I'm walking along, I keep looking for some cool nature stuff to kind of photograph. And then all of a sudden, I see it. I see this bear. Okay. So I see this bear and I'm like, oh, whoa, all right, let's not get eaten today. And I take some pictures of the bear though. And then I decide that maybe that's enough excitement for one day. Okay. And so I turn right again. All right. So I was going south a mile. Now I've gone west a mile. Now I go north a mile. Okay. And after going north a mile, I walk back in my front door. I put my camera away and I relax. All right. Hopefully, something doesn't sit well with you now. But here's the question. Here's the real riddle. What color was the bear? Okay. So I'll kind of leave you to think about that, and we'll just kind of jump in here. So before we can even talk about these terms, position, displacement, distance, speed, velocity, acceleration, all this stuff that you've heard before, we got to talk about two words. And the first one is the word scalar. I know that sounds a little weird. So scalar. Now, scalars, these are quantities. So a quantity that has only a magnitude. Now, when I say magnitude, I really just mean size. Like, how long is it? That's it. Or how big is it? But let's zoom in even a little bit more. There we go. But no direction. So, for instance, maybe I just say like 5 paces, 5 steps. That's it. You're like, where? Which way? I don't know. The other thing that kind of contrasts this is a vector. I don't mean the evil villain in Despicable Me. This is actually a quantity. That has both a magnitude, again, that size, and a direction. So, for instance, this instead would be 5 paces north. It has a direction, or to the right, or it has some way that kind of indicates to you which way it's going. And so in physics, a lot of things are vectors, a lot of things are scalars, and we kind of have to know the difference between them, all right? So let's look at what the heck position is now. Position. This is really just a scalar, in all honesty. So it's a scalar, and it really represents just the location. The location of an object. Something, right? And typically this is in reference to some coordinate system. So typically, like your math class will use X and Y. We won't use anything. We'll just use those in this class, but sometimes in later classes, maybe it's like X and Y and Z. So we'll just say X, Y, Z, kind of all of 3D space that we actually get to occupy and live in, which is pretty awesome. It'd be a bummer to be like a flatlander, like a 2D world. So here we go. Position. Let's say I have some ant. I have a fire ant here, and my little fire ant kind of jamming along there, and it's at 1-1. So there's my ant's position. Cool. Awesome. And then maybe we just say that, oh, later, let's say that, I don't know, maybe my fire ant is just at some other position. All right, maybe my fire ant later is just at the position 4-1 instead. All right, so there, we just have two different positions, or maybe even, and again, I said we won't actually use this in this class. I'll never have you actually graph something on a 3D graph, at least not seriously, maybe for fun later. But this fire ant over here would be in like a 3D plane. You're like, wait, I don't get it. Where the heck is it actually? Well, the idea is you kind of drop a little vertical line down here. You go, oh, it's there in the Y, and it's over there in the X, and then it's over there in the Z. You know, you can kind of have an idea of where the heck this fire ant is. So actually, when you're looking at a XY graph like this, it's actually like you're staring down the Z axis, which is kind of a trip. I know, right? So it's really like your eyeball. There's an eyeball, and you're kind of looking down, and you're actually looking straight down the Z-axis, and that's actually how we get this view of XY that you typically learn in like a math class. So that's kind of a side though. Let's look at the next one now. So now let's look at distance. Now, distance, this one is also a scalar. And distance really is just how far something has moved. That's it. Or how far an object has moved. That's it. It's simple. So if we look at my example up here above, I don't know. Let's say that my fire ant went from 1-1 to 4-1. Well, how far has it moved? Well, it's gone along this kind of path. It's moved 3 units. We've gone from 1 to 2 to 3, or from 1 to 2, and then from 2 to 3, and then 3 to 4. So we've moved 3. So here really the distance is 3. So the distance is 3, whatever the heck those units are. All right. Now, let's look at displacement. Now, displacement, we finally have a vector. Okay, so what that means is it's really how far an object has moved from its starting point. How far an object has moved, from its starting point. Okay, well, let's again look at the example from above. Well, here, our fire ant started at 1-1, and now it's at 4-1. So how far has it moved from its starting point? Well, the displacement here would be 3 to the right. Okay, so maybe you think I'm splitting hairs here. These are almost the same exact freaking thing, right? So what the heck? What is up with that? Well, let's look at an example that hopefully makes it a little more kind of abundantly clear, maybe a little more of a challenging example. Not really challenging, but something that kind of proves and indicates really the significant difference here. So let's just say that I have, again, kind of my graph here. I don't know, maybe just go 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, something like that. Here's X, here's Y. That's typically how we do it, right? And let's take my fire ant again. Okay, so we got the fire ant. Let's start our fire ant out right here at 1-1. Okay, cool. So let's say the fire ant starts out there, and moves along this path. Let's say he goes right here, and then he goes up here, and then he goes there, and then he goes there. And actually, just for sake of me being able to write, no, we'll leave it. So let's look at this. Well, we've gone 2 units here. We've gone up 1, 2, 3, 4, 5 here. And we've gone back 2 here. And we've gone down 5 here. Well, 5 and 5 is 10, plus 2 is 12, plus 2 more, that's 14. So the distance, how far the ant has moved, right, is 14. So we have a distance of 14 units, whatever the heck these units are. But let's look at the displacement. Well, it's how far the object has moved from its starting point. Well, isn't my ant ending where it started? So our displacement is 0. 0. And there isn't even a direction, because how do you go 0 north, right? You just don't. So that's it. Now, in other words, here's kind of a nicer way that I usually show. Let's say this is point A. Let's say right here, this is point B. And let's say that, well, obviously from A to B, we have, oops, right there. That looks pretty good. We go right along here. So I would say that kind of displacement is just the straight line distance. Displacement is really kind of as the crow flies, if you understand that old school phrase. It's kind of like just how far in a straight line. But let's say that in reality, you were going along and you went up here, and then you kind of went over here, and you almost came back, and then went over here and there, and then you finally ended up there, right? This would be the distance that you actually had moved. Okay, so that's kind of the difference between distance and displacement. All right, cool. So let's keep going here. And actually, maybe we just keep using blue. That sounds kind of fun. So let's look at speed. All right, now speed is a scalar. That means it just has a size. It does not have a direction. And really, it's how much distance is traveled. How much distance is traveled in a certain amount of time, or per unit time. Per unit time. So then I'm going to put a comma here, even though we should put a period. And here's the way that you probably would hear it or say it, like on the street. How fast something is moving. That's probably the easy way that you would hear it. And maybe you're thinking, well, I encounter speed all the time because I go on in the car and I see the speed limit sign, right? So well, here would be an example. 65 miles per hour. So we have distance traveled, that's miles, per P, and then unit time, hours. So in 1 hour, you go 65 miles. But really, in our physics class, we won't use miles. We might say, instead, let's say it's going 65 meters, so M, per second. So it's meters divided by seconds, meters per second. Okay, so that's kind of an easy idea for that. And I'll say that we use meters per second. And actually, I'll just write that in words, meters per second. Okay. Now, here's the even more kind of cool, important thing, and this will relate to our lab we last did and upcoming activities and labs and questions and things for the future. Really, I would say that actually, I'll wait and do velocity first, and then we'll kind of come back to this. So let's look at velocity here. Velocity. Now, velocity is a vector. That's kind of convenient. They both have the v. Now, velocity is just speed plus direction, which is funny because a vector is literally just something that has a size and a direction. So it literally just is adding the direction part to speed. That's it. So this would be like, as an example, 65 miles per hour north. It has a direction. Poof, it's a vector. Easy stuff, right? Now, this is why it's not a velocity limit when you're on 101. Let's say you're going down to San Luis Obispo, right? You get on 101, you're going south, you're going 65. If it said 65 miles per hour south, you could never turn left to right without breaking the velocity limit, right? That would be a total bummer, right? You want it to just have a speed, because then even if the highway curves a little bit and it kind of goes over a hill, or you're going up the grade and it's not perfectly south, you're not breaking the law. Okay, so kind of easy, pretty straightforward. And typically we will use, I won't use a different symbol between speed and velocity, honestly. We'll just use the symbol V. And actually, to kind of help you out for the future, we'll say right here that velocity is really, and I'm just going to take this part right here, this how much distance is traveled per unit time. We're going to put it in like math terms, like a little equation that you could use. So we'll say that velocity is the change in distance, so delta x, that's change in distance over the change in time, okay? And now for my calculus folks, we'd say that v is dx dt, okay? So it's actually just a time derivative of the distance. That's it. But if you're not a calc person, don't worry about it. So here's the important part, though, for everyone. Really, this means it's the slope of a position versus time graph. So that's actually really important. If you have a position versus time graph and you just figure out what the heck the slope is, you poof, suddenly know the velocity, which is pretty freaking awesome. All right. And the neat thing is that it is velocity you would know, not the speed, because it would include a direction, because you can have a positive slope or a negative slope. And that actually kind of implies the direction for us. We'd say, oh, in the positive direction or the negative direction. Okay. So now I know you're probably wondering about why I have this freaking Ghostbusters car here, right? So we could actually do a kind of an example. We could kind of write one down here. That's what I originally put it there for. Now I just like that it's here because I'm a big Ghostbusters fan. So let's say that we have, actually, we'll come back to it. We'll come back to the Ghostbusters vehicle, okay? So I'm going to look at our last term. We'll kind of look at these graphs. We'll talk about maybe our Ghostbusters a little bit, and that'll be it. So, oops, sorry about that. Little backup alarm going off in case I slept through everything. So let's look at our last term, acceleration. Okay, now acceleration is a vector. And all it is how much the velocity is changing, or the velocity changes per unit time. Or in other words, how much it speeds up or slows down. So maybe you're looking at this and going, hey, some of this terminology seems similar to the speed thing. We have how much distance right here, right, is traveled per unit time. And now we have how much velocity changes per unit time. And well, maybe you're going, well, speed was a slope thing. Acceleration maybe is a slope thing. You're totally right. And if I jump the gun on that a little bit, that's okay, because we're going to look at that right now. Now, it has a direction. It totally does. It has a direction. Okay. And we'll look at this a lot later in future units, kind of how the heck we figure out the direction for acceleration. But I just want you to get the idea that it has a direction. Okay. That's the important part, really. So, what this would mean then is kind of like our velocity part here. Okay. We're going to have then that acceleration is just the change in velocity over the change in time. Or again, for my calculus folks, acceleration is just dv dt. So if you're ever given like some function for the velocity, just take the time derivative of it and you poof have the acceleration, which is pretty neat. So really, this means it's the slope of a velocity versus time graph is the acceleration. So now I want to show what I actually mean, okay? Let's say that I go back, I have a little battery powered car, and it happens to be a wicked cool Ghostbusters car like this one, okay? And we do the same thing that we did for the lab, and I take some data on it, end up getting this, okay? I get that every second. I look at how far it's gone and I plot these different positions for every second. And I know that my dots don't perfectly match up, and that's okay. So let's say that I put it on the computer and my computer gives me this as my equation for it. And we go, wait, okay, how do I figure out how fast it's going? Well, maybe I could look here and I could say, maybe this is like 35 or something, and it's over 1. So 35, and we know that speed is distance per time. Well, if it's gone 35 centimeters, that's what this one actually would be, over 1 second, that would tell me I'm going 35 centimeters per second. That's a change in distance over time, kind of like miles per hour. That would maybe be the speed. And then you could figure out whatever the heck this distance is and divide it by 2, and this distance and divide it by 3. And we would keep doing math, is the whole idea, what I'm trying to get across here. We could keep doing math and figure out how fast it's going. Or if you have the equation for it already, well, this thing is a y equals mx plus b. That means that this little 34 here, right, is the m. That is the slope, right? Well, didn't we just say above that the slope of a displacement versus time graph is the velocity, how fast it's going, and the direction, right? Well, poof, we suddenly know that this is the velocity. It's going 34 centimeters per second, all right? That's it. So just by looking at this, I can tell that. Now, what if it was actually like some shape that went like this? Well, we would have the slope is changing, right? As the slope gets, so right here, the slope, and I'll use a different color, I'll use yellow. Here, the slope is like pretty flat. And then here, the slope gets steeper, right? And then here, the slope gets steeper still and steeper still. Well, this would be a car that's going faster and faster, right? Because the slope is getting bigger and bigger. The speed is increasing every single second. In other words, it's accelerating. This would be like you taking off from a stoplight, is what I'm trying to get across here. But in the case of this one, as we have it, and I'll leave that just in case. So this would be for it accelerating. Okay, so let's not look at the accelerating one. Let's look at this first one. So this is a constant velocity. This actually right here, my straight line, since it's a constant slope, and the slope represents the velocity, right? Well, that tells me, okay, we have a constant velocity. So now if I forgot about the direction part, and here the direction's positive, right? Or actually, let's just change this. Let's just make this velocity. And so I should have my units, centimeters per second here. This would be centimeters, okay? And then we'll think about what the units are for the acceleration one. So we have seconds there, we have seconds there. So now, how does the velocity graph look? Well, if we're basing it on this first graph of the distance, right? Well, the slope is constant. That means that the velocity is constant. So that means that over time, my velocity is not going to change. That's what constant means. So all I'm going to do is get my ruler and just say that, well, the way I draw the velocity over time from this first graph is I just have to draw a straight line. And what is the value for it? What's the number for it? Well, we already know it's 34 because that's what the velocity was here. That's what the slope is of it. So that's kind of neat, right? So we have a constant slope here. It's constantly going the same distance every second. Well, that means the velocity is a constant value, okay? So let's think about this now. So really, all we've done then is to go from this graph to this graph, we've taken the slope. Kind of following just what it says up here. So it's a slope. Great. So now, let's get the acceleration graph. Well, it says here it's the slope of a velocity versus time graph. Well, what is the slope of this velocity graph? If it's flat like this, it's horizontal, the slope is 0, right? So I kid you not, all I have to draw for my acceleration is that it's just at 0. So again, all we did is we took the slope. So we've taken the slope. Okay, that's it. To go from distance versus time graph to a velocity versus time graph, we just take the slope. And if it's constant, well, it's just a constant line. Then we take the slope of a velocity time graph, and that gives us the acceleration. So let's think about the units, though. What the heck are the units for acceleration? Well, if velocity is the change in distance over the change in time, that gave us like centimeters over seconds, right? Because we changed distance over time. But then acceleration is the change in velocity over the change in time. So wait, isn't that going to give us this velocity is going to go there, right? And then we still have seconds down here. So we're going to have centimeters per second over seconds. It's how many centimeters per second, how much the speed or the velocity changes every second. If your car is going faster and faster, you're going at a different speed every second, okay? So maybe you're wondering what the heck about this second graph that shows it's speeding up. Well, you maybe would have something like, I don't know, like this. Because here the slope is getting steeper and steeper and steeper and steeper as we look at the yellow little dashes, right? So my velocity is increasing and increasing and increasing and increasing because the slope is increasing and increasing and increasing, right? So, well, if the velocity is increasing every second, wouldn't that be a line something like this where we see the velocity increasing, right? Well, then if we took the slope of this, well, we would get something that's not 0, right? You could take your ruler, you could look at whatever the heck the slope is, find your rise over run if we do the numbers and stuff, right? And then you'd get some acceleration that, since this slope of this is positive, you would just get some positive constant acceleration. And it would be constant for the acceleration because the slope of this line would be a constant, okay? So that's it for now. Please write down questions, comments, where you're getting stuck, all right? And then we can kind of go over and answer all the questions next class.